Good day. I am JM, an ID 120 student taking up civil engineering, and I'll be teaching ENGMEC3 quiz number 1. Now, let us move on to the next problem. So, the next problem is quite complicated as it is not of the same process as how we would solve the first item, but this would fall under the second topic, which is deformations. So, the distributed loading is supported by 3 suspender bars. AB and EF are made of aluminum while CD is made of steel. If each bar has a cross-sectional area of 450 square millimeters, determine the maximum intensity W of the distributed loading so that an allowable stress of sigma allowable for steel is equal to 180 megapascals in the steel, and sigma allowable for the aluminum is equal to 94 megapascals is not exceeded. As, we also know that the Young's modulus, or E, of steel is 200 gigapascals, while E for aluminum is 70 gigapascals. Assume ACE is rigid. So we know that it is rigid, and we know that the total distance between the between the 3 bars is 3 meters. So if we have a distributed loading here, this would usually be equal to something kilonewton per meter. So given this information, we can apply it at the center, which would be pretty similar to how you would apply something in our ENGMEC1 when we get the centroid. It's applied at the center, right? So for this would be a total of 3W, considering that the length is 1.5 plus 1.5 times the intensity. So the intensity is the loading, and we also know from the figure that the rigid bar has 3 supports that would be extended because of the weight of application. Therefore, when we have downward forces due to the distributed loading, A, C, and E would have forces directed upwards. So let's label this as FAB, this as FCD, and lastly this as FEF. So we also know the components or the materials used. So it's important to also take note of that. So let's first develop moment equations. So first off is the moment at C. Why do we need to determine our moment equation? Well, it's important to know this because we want to ensure that it is in equilibrium. So when we talk about equilibrium, we know that the moment or the summation of all moments along one point must equate to 0, and the summation of forces along any axis, may it be the x or y axis or another imaginary axis such as the one that was made in the previous example, would equate to 0. So the approach here is to look at places or points where you can get lower lower equations or equations that have smaller amounts of unknowns. So first off, let's try this. So at C, we will eliminate the effect of our 3W, and we would also eliminate the effect of our FCD. So that's perfect for getting smaller amounts of unknowns. So this would be FAB times 1.5, and it's applied here. So if you rotate it due to an upward force, it would rotate clockwise. So let's make it positive. While for E, or the force EF, it's rotated counterclockwise due to the upward force. Therefore, for our force due to force at EF, we would multiply it by 1.5. then this would be equal to 0. Let's cancel our 1.5s since the distance was the same, and you can just divide all by 1.5 and not get any different values. So we would be able to say that FAB is equal to FEF. We also know that it is made out both of aluminum, so let's just call this force F or F aluminum. You can choose naman which you would prefer. Next, let's get the summation of our Fy forces or forces along the Fy or along the y-axis rather. So let's set up a convention where the positive values are those that are upward while negative are those that are downward. So for the moment C, let me just add here that our convention is positive for clockwise. So for the summation of y-axis, we have here 2f because FAB plus FEF is just F plus F, which is also equal to 2f, plus FCD minus 3W equals 0. We can't do anything else about it because we're already, this is already simplified. Let's label this as equation 1. Then we know that the deformation in A is equal to the deformation in C. And the deformation in C is also equal to deformation in E because the same amount of loading is applied to all parts. And since it's a rigid bar, it means that whatever you apply, it would be distributed equally. So therefore, for our compatibility equation, so compatibility equation, the deformation in A is equal to the deformation in C. This means that the force at A times the length at A over the area, cross-sectional area of A and the Young's modulus or modulus of elasticity at A is equal to that for the E. So, for the C. So, let me just complete the formula. This is taken up from the formula that deformation is equal to FL over AE. So, don't forget about this formula as it is a very important formula. Then we have here, or we can input our values. So F or the L, the length of A, the length of C would just cancel out. The cross-sectional area at A, the cross-sectional area at C would also just cancel out. So we can cancel it out here, cancel out because it's just of equal lengths. Then we could focus on this relation. So f of A is just F. Oops, let me just change it. Then the elasticity at A, since it is aluminum, we will use 70 times 10 to the 9 since it's gigapascals and we want to ensure uniform units. Let's convert it to pascals by multiplying it by 10 to the 9th. For FC, it's just F sub CD times, since it is steel, we will use 200. So simplifying everything, we would get our second equation as F is equal to 0.35 FCD. So let's label it as equation 2. Now, we want to assume first the failure to happen at FAB and FEF. So by it failing there, we will know that there is a relation, or the simplest relation is sigma is equal to F over A, where sigma is our allowable stress and A is our cross-section. So substituting or converting this equation, so we will get F is equal to sigma allowable for steel, or for aluminum rather, since we will assume failure at AB and EF, times the area. So this is equal to 94, since it's in megapascals, 94 megapascals is 94 times 10 to the 6th. Then we will also convert our area from 450 millimeters squared to 450 times 10 to the negative 6 square meters to assume uniformity again. So this would result in a value of 42,300 newtons, which we can just say is 42.3 kilonewtons. Now, we know our value of F. So again, FAB is equal to F, which is also equal to FEF. Using equation 1, let me encircle it for you to get a glance of what it is. So using that formula, we will be able to get, okay, so after determining F to be 42.3 kilonewtons, we can use equation 2 to determine our FCD. So FCD is equal to F over 0.35. So this would mean that FCD is 42.3 kilonewtons over 0.35, giving us a value of 120.86 kilonewtons. Now, wait, let me just put here that we used equation 2. Then we used here the formula for stress. Lastly, we can get W, since we already have the force at CD and the force at AB and EF, which is just F, using equation 1. So equation 1, 2 times 42.3 plus 120.86 minus 3W is equal to 0. Using our calculators, we can simplify this as W is equal to 68.49 kilonewtons per meter. And now we highlight it because it is already our final answer. Thank you so much for watching. You may also avail syntax tutorials by scanning the QR code flashed on your screens. Once again, this is JM from Syntax, paving your way to excellence. Thank you so much for watching. You may also avail syntax tutorials by scanning the QR code flashed on your screens. Once again, this is JM from Syntax, paving your way to excellence.